Assalamualaikum and hi guys, my name is Mirhana and we are from Group 4. We're going to explain on this Group 4, which is Refrigerations, VCR. First, VCR is defined as cooling the temperature environment for space and transferring it elsewhere. And this system may be found widely in homes and houses, such as air conditioners, which remove heat from our rooms, and refrigerators that store our food. Objectively, this experiment was conducted to the coefficient of performance, COP, the corporation's cooling system itself. And according to the law of conservation energy can either be destroyed or created, but can only be converted from one form into another. Therefore, the heat is dissipated to the surroundings at low temperature. A refrigerator is used to transfer heat from low temperatures to a higher temperature region. And refrigerators are cyclic devices, and the working fluid used in the cycle is called refrigerant. This vapor compression refrigerations consists of four main components, which are compressor, condenser, valve, and evaporator. While the evaporator pressure should be low, whereas in the compressor, the pressure should be high. Similarly, in the condenser, but not more. For the valve, as the pressure should be lower and back into the compressor. This theory will be further explained by our next presenter, Ms. Fatina Jiha. Thank you.
Thank you, Mira, for her presentation just now. So I will continue our presentation with objective and theory. So our objective for this experiment is to determine the coefficient of performance COP for vapor compression cooling system. Next, theory. The vapor compression refrigeration cycle is thermodynamic cycle to generate refrigerating effect with the use of compressor, condenser, expansion valve, and evaporator. It is a compression process. This process is basically a process where working fluid absorbs heat from the surrounding or low temperature space and reject heat to the atmosphere at higher temperature surface. This process requires work, which is W, to be supplied to the system as depicted in figure 2 at the right side. Refrigerant flows through the compressor, which raises the pressure of the refrigerant. Next, the refrigerant flows through the condenser, where it condenses from vapor form to liquid form. After the condenser, the refrigerant goes through the expansion valve, where it experiences a pressure drop. Finally, the refrigerant goes to the evaporator. The refrigerant draws heat from the region that is to be cooled. The vaporized refrigerant goes back to the compressor to restart the cycle. So, next, the equation for this experiment is coefficient of performance COP can be calculated based on the following equation, which is COP equal to desired result divided by required input. But for the refrigerator, the desired result is the heat absorbed at a low temperature, and the required input is the net work into the device. So the equation becomes COP equal to cooling effect divided by work net in. And from figure 2, we can conclude that the heat absorbed at a low temperature is equal to Q2, and the net work is into the compressor is equal to Q1 minus Q2. So our final equation, COP equal to Q1 over Q1 minus Q2. So I think that's all from me. I will pass our presentation to next presenter. Thank you.
So for this experiment, the apparatus that we will need is Refrigeration Cycle Demonstration Unit R633PA Hilton using R141B refrigerant fluid. And now for the methodology. At the initial of the experiment, the following components such as evaporator, condenser, compressor, expansion valve, voltmeter, water flows in and out, and the flow of the fluid R141B as depicted in figure below are identified. The thermometer for each position is observed and do not blow out the vent valve. And the picture here is components in refrigeration cycle demonstration unit R633PA Hilton. Then operations were launched and the readings are recorded. The valve is open as illustrated in figure in the right side, and the water pipe was open and the water flow rate to the evaporator was set as 19 gram per second. And water flow rate to condenser is maximum. The main switch is switched on. The cooling system is allowed to be stable approximately 10 minutes, and the parameter listed in table 1 were recorded. The experiments are repeated by changing the flow rate of water to condenser between 0 to 20 gram per second for 4 times. And then, as for operations termination, the main switch is switched off and the water supply pipes are turned off after 1 minute and the valve are closed to the shutdown position after 1 minute as depicted in the figure in the left side. That is all for apparatus and methodology. I will pass to the next presenter. Thank you.
I'm Sana and I will present the data and discussion part. So, this is table 1, data for vapor compression refrigeration. So, all the data get from the experiment that already run. We are using this data to complete our discussion part. Okay, so, for the discussion, we need to calculate the rate of heat transfer that occurs in the evaporator and the condenser for the 5 test run and discuss the results. First, we need to know the rate of heat transfer in the evaporator. Then, to know the rate, we use this formula. Q equal to M delta H, where the mass flow rate of the evaporator is constant, which is M is equal to 26 gram per second, and it will convert to 0.026 kilogram per second. Then, to get the enthalpy, it can be obtained by doing interpolation based on T1 and T2 for every test using the steam table. So, from the formula, we can see here, for test 1, we get 63.44 kilowatt, and for test 2 and test 3, we get the same value, which is 63.34. And for test 4, we get 63 and 31 kilowatt. And for test 5, we get 63.27 kilowatt. Okay, next, we will proceed with calculating the rate of heat transfer in the condenser by using the same formula, which is Q equal to M delta H, but here we can see the mass flow rate for each test is different. After calculating, we will get the Q1 is negative 62.83 kilowatt, Q2 negative 55.14 kilowatt, Q3 negative 45.46 kilowatt, and Q4 and Q5 we get negative 33.47 kilowatt and negative 28.68 kilowatt respectively. Okay, next, since the rate of heat transfer in the evaporator and the rate of heat transfer in the condenser is defined as magnitude, so it is a positive quantity. Therefore, the efficiency of refrigerator, which is expressed in terms of the coefficient of performance (COP), should be known. So here we can see the formula of COP, which is modulus QL divided by QH minus QL. So, from the above calculation, we can see that the value of the coefficient of performance increase. Even its value increase, it does not exceed the unity, which is its value less than 1. Okay, so we proceed with the next question, which is we need to explain the effects of changing the condenser flow rate of T1 until T6 to compressor power. And we need to draw the graph and discuss the results obtained. So we can see here the table 2, data of condenser flow rate and its temperature from T1 to T6. From this data, we need to plot the graph. So we can see here, this is the graph show the temperature from T1 until T6 versus the flow rate in the condenser for all 5 tests that run in this experiment. From the graph, we can see that the temperature will affect the flow rate in the condenser. It shows that when the temperature increases, the flow rate in the condenser decreases. When seeing the graph, we can consider that this statement, the increase, the decrease is valid for temperature from T1 until T4 and T6. It is not valid for T5, maybe due to some error occurring when running the experiment and making the value of T5 not accurate. Okay, next we can see here the table 3 data of condenser flow rate and compressor power and the graph. So based on graph 2, the graph shows the compressor power input against the flow rate in the condenser of T1 until T6. It shows that the compressor power decreases during test 1 and drops drastically during test 2, which is from 171 watt to 168 watt. Okay, during the experiment, an error that might occur in this experiment is the value of compression power, in which these values keep changing with time. Thus, the value obtained is not accurate. To increase the accuracy of the data taken, take the average values of that temperature for T1 until T6.
In a nutshell, the value of the coefficient of performance of the refrigerator, COP, increase with the increasing value of the rate of heat transfer in evaporator. We can conclude that compressor power decreases as the flow rate of the condenser increases. Thus, the compressor power is inversely proportional to the condenser flow rate.